Hey everyone, this is FixReef, and today we have this little guy up for repair. This is an Apex FMM module or fluid monitoring module. Or in all docs you will find it as a WMM, which I guess stands for water monitoring module. This is a small add-on module to Apex that allows you to do things like attach sensors for leak detection or attach fluid valves. It connects to Apex over the typical Aquabus port that looks like a USB port. But it also has this couple of ports on this side. So this port here is the power jack. That's for the 24-volt power input. That's so that you can have a 24-volt controlled outlet, similar to EB832, where you can have a one-link 2-pin output where you can switch it on and off with a relay, similar to what you do with the 110-volt AC outlets. So this unit came with a problem that it sporadically disconnects from the head unit over time and messes up with some measurements that are being displayed on the infusion. And it's clear to the customer that this device is causing the problem because they were able to isolate it to this device, unplug everything else, plug just this one in, no additional fluid sensors or anything else connected to it, just Aquabus, and also the 24-volt power input. And it's somehow not working. So we're going to take a look at it today and see what's going on with it, what's wrong with it. First, before we take it apart, we will try to see if there is a problem with the right way with this module. So first, I'm going to try to connect it to my Apex head unit for testing purposes over Aquabus. We'll pick a port. The light is blinking green and it's turning green, meaning that it's solid green, meaning that it's connected to the head unit. So far, so good. I'm not seeing anything being disconnected right away. It's not acting up. So far, so good. Okay, the next test I'm going to do is I'm going to disconnect the Aquabus port and instead connect the 24-volt input off of my lab power supply to see if it's going to be able to power the unit up. So I'm going to give it about 24 volts. And I'm seeing right away that the status LED is not on. On a good FMM unit, if you plug in the 24-volt power in, they kind of each can be used interchangeably, either power off of Aquabus or 12 volts or power off of the 24-volt power supply. You're supposed to see LED status. Obviously, since Aquabus isn't connected, it wouldn't be able to connect to the head unit. But at the very least, it should be able to start blinking some type of LED over here stating that it's waiting to be connected to Apex, and it's not connecting to Apex. So we're going to take it apart and see what's inside. All right, so that's the inside of the board, or inside of the unit. Let's see if we can get the board apart. Apex loves the glue everywhere to hold things together, so we'll have to... Well, before we take it apart, let's take a look. Oh, I think I already see the problem. I'm not sure if you guys can see it, but let's walk through a few components here. Let me zoom it in so that you can see the entire board. Now you can definitely see where the problem is. But let's start here. So Aquabus input, 24-volt input. Aquabus, right over here, has the CAN bus transceiver chip. That's the same chip installed in all of the units, including the head unit and all of the modules and the EB832 and so on. Some power circuitry here to go from 12 volts to whatever this main CPU is going to consume, 3.3 or maybe 5 volts, I'm not sure. This is a big relay. That relay is going to shut on and off the one link port that's here. That's the 24-volt port. And this is the 24-volt input. It's got again the power circuitry here. And this chip over here, you can see all brown. That is a buck converter. This whole setup over here between capacitors, resistors, the inductor, and the larger smoothing capacitor, this is the power circuit to take the input 24 volt coming in and convert it into something again that's going to be usable by the main CPU in case the Aqua bus isn't connected and is not powering this unit. Right now, it is clear to me that this is likely the controller that failed, the controller that burned, and it will have to be replaced. Again, in my previous videos, I already had several discussions about these buck converters. Apex uses them very frequently in a variety of modules and primarily in EB832. This is not exactly the most powerful buck converter in the world. It does not provide a lot of power. In this case, it doesn't need to provide necessarily a lot of power for just this one module. But the problem is that the power off of this buck converter is being shared not just with the controller on this board that doesn't really need much, but it is also being shared over Aqua bus. Imagine a situation where your EB832 is no longer providing power for whatever reason. Everything is daisy-chained through Aqua bus ports throughout the entire system. Maybe you have 5, 6, 7 different modules. The head unit connected, the display is connected to it. Everything's daisy-chained over Aqua bus port. And now, this tiny little controller is going to power all of those units in case EB832 is disconnected, power off of the head unit is disconnected. Now this one unit is going to be responsible for providing power to all of the modules in that chain, which is insanity. It's pure insanity to do it this way because this chip is not capable of handling high loads. What I'm going to do today is I'm going to not only replace this module, replace this controller, replace this buck converter, but I'm actually going to upgrade it to a higher quality automotive grade component that's supposed to last longer and able to handle higher loads than this simple component here. All right, now let's take it out. I'm just going to cut the glue. As much as I can. All right, we have the board out. Let's see if there is anything on the other side. And there is a poor diode connected to this. I've seen diodes like this on EB832s connected on the 24 volt. This is for to protect the circuitry. This was definitely an afterthought. All right, let's look at this under the microscope. Okay, so this is our controller that failed. This is our buck converter that failed. You can see that the model of it is M. Let me see if I can make it a little easier to see, but it's 34063A. Let me bring up the data sheet for it so that I can show you what we're talking about here and I can explain things. Okay, so this is the data sheet for this buck converter. There are several variations of it exist, but let's take a look at the specs. All of them have about the same specifications. However, operating, ambient, temperature range, and operating juncture. So 34063s can operate from 0 to plus 70. Others, 33063, can operate at high ranges temperatures. So this particular unit is the cheapest of them all, 34063, that operates. It's still within 0 to plus 70 Celsius is still a pretty good range, but the problem is that if it gets stressed by the amount of power that it needs to provide, then the temperatures that it can operate at safely tend to matter. So what I'm going to do is I'm going to upgrade this unit to 33063 that is made for automotive industry with the highest possible operating range of -40 to plus 125 Celsius. This will give us the best chance of this controller actually making it through stresses, although it's not going to obviously guarantee that it's going to survive a very high load for an extended period of time, because that's what essentially kills them. Okay, let's go ahead and remove this. So I'm not sure if it got itself welded when it overheated like this, if it got itself welded into the board. Hopefully it didn't. Let's remove, clean things up, and see if we can replace it. I'm going to use my hot air for this. It should be a fairly straightforward task. I can see that some solder already coming from under the chip. It's definitely warm, but it's not coming off easily. And there it comes. All right, the area does not look good at all to me. So we're going to see if there was much of a damage. Actually, let me take off the remaining solder first. A little bit more flux. All right, pads on this side look good. But the whole area is nasty. Okay, let's see if we can clean this up. I'd like to see the other side, the back side of this controller, because this is a lot of I'm not even sure what it is. But whatever it is, it's all pretty much gone at this point. It's almost like they tried to glue it. And I have to be careful removing all of this because I don't want to damage the existing traces beyond the damage that's already been done. You can see the board is the board layer is flaking off in the center, which can only mean one thing. This controller endured some fairly significant heat. Of course, it could be that the heat is because the controller just or the buck converter just overheated, or it could be because it shorted and burned. Either way, this stuff is nasty, and it is unfortunate that it happens to so many units from Apex. All right, this looks marginally better. As you can see, a couple of pins or a couple of traces here are actually connected by up at the top by these two pins, which is to be expected. That's the way how the buck converter is supposed to be wired. What happens here is that these two resistors over on the right, R4 and R9, those are voltage dividers that basically tell the buck converter what the output voltage from 24 volt is supposed to be. So this is probably converting things into something like 3.3 or likely 5 volts output. And then there is a capacitor for the input voltage. And then once the 5 volts created by the buck converter, it needs to be it's pulsing, because buck converter, what it does is it basically churns the 24 volts input on and off, on and off, on and off. But that's not how you power electronics. So instead of having a 24 volts on and off at a certain frequency, then this inductor and then following by the capacitor, they smooth the 24 volts on and off, and they average it out into whatever is necessary. In this particular case, likely about 5 volts. And that's how this whole thing works on every single one of them. You know what I suspect is actually happening here? This gooey stuff is the glue that was used, if you remember, to hold the edges of this board to the plastic. I think when they were assembling it, they dropped a drop of this glue on the controller, on the buck converter. Now guess what is going to happen if you have a component that tends to overheat when you encapsulate it into this glue with absolutely no air circulation? That's right. It's going to overheat fast, and it's going to blow up. And that's why we see so much damage on this board. That's all right. We'll make this FMM happy again. So before we go any further, let's apply some fresh leaded solder to the pads. And let's get our brand new, improved, and much stronger buck converter. Okay, this is going to be our new buck converter that's going to replace the old one. Fits identically onto the pads. All we need to do is just apply a little bit of flux to help solder flow. And let's put it in place. you can see that there is additional glue coming out of all kinds of directions here. So glue was definitely the reason this whole thing failed, plus additional load on the unit. Okay, let's clean this up as much as we can, although understanding that some glue is still lurking around. I'll try to get most of it out of here. I would like to get as much of the glue from under the um, coil as possible as well, because the problem is that this area will heat up once you provide enough power to it and provide enough load to it. As it heats up, this glue is going to start melting again. As it melts, it's going to potentially flow under the new buck converter again. And if it does, it's going to cause this trouble again. So I'm going to get rid of as much of this glue as possible. Okay, this looks good enough. All right, let's see if we fix the problem or if there is anything else. Okay, now we're back. We have the unit all set up. Now we are going to attempt to plug in the 24 volt power input and see if the fixed buck converter actually fixes our problem. Oh, and look at that. The green LED is flashing. Green LED flashing means that the power is going through the circuit as expected, and it's waiting to be connected to an Apex. Let's connect it to an Apex and see if the power, if the green LED switches over to solid green LED. And we have a solid green LED. Well, I will do some testing behind the scenes with the functionality of this unit once I assemble it. All right, so let's put it back together. I'm going to use my hot air to essentially melt a little bit of this glue so that it holds things in place. That's the favorite compound selected by Neptune to hold their components together. So all right, it's gooey. All right, it can dry up. I'm checking to see if there is any other glue that's sitting on components anywhere, and it looks decent enough. All right, the top cover. Okay, now let's do some real testing on this. I'm going to connect the 24 volt power supply to it. I'm going to connect Apex head unit. Wait for it to initialize. Good. Now I'm also going to attach my test cable to one link and make sure that it can handle a reasonable load. Okay. Now I'm going to set up my electronic load. so that you can see. All right. So right now, there is no voltage output at all out of the one link on this module. So let's plug it in. Okay, so this is my setup with the FMM module connected. This is actually going to be, I have a couple of them. 9 is the one that I currently have. So currently the 24 volt link is off and it's providing 0 volts. Now we're going to turn it on. We hear the relay click and it's producing about 23.74. That's about what my power supply gives it. In fact, I can probably bump it up just a little bit to give us approximately what we need. Okay, that's going to be enough. Okay, now let's give it some load. Now, okay, let's leave it at about 500 milliamps. It's not a whole lot, but it's enough. That just tests that the relay works and it's capable of providing that much current over it. The buck converter is not really involved in creating this 24 volts because that's a direct through output from the power supply. That's the input of 24 volts into the output that's 24 volts. We're going to test the output in a different way. But for now, it looks like the 24 volt output works. So we're going to disconnect the load. I'm also going to shut off the 24 volt link. It's no longer needed. Now, instead of testing the 24 volt, we're going to use the same tester to test the Aquabus output. And this is the one that's going to actually stress the buck converter, because now the buck converter is going to be responsible for providing 12 volts. All right, let's connect our load. We see that about 11.5 volts are being produced. Let's apply some reasonable load to it. Actually, 5, more like 400. Even 400 is a little bit too much. I think for this one I would give it, you can see that the voltage is truly dropping on it. So 200 is what I would probably give it at best. And it seems to be producing 200 no problem. The voltage stays fairly solid. Okay, so this tests the buck converter. The buck converter works, it provides power output. It's not supposed to, it's not actually, well, it does not actually need to provide this much amperage. The whole point of the 24 volt input is so that you can have a 24 volt accessory link output and not to provide power for the Aquabus ports. But the way it's wired, if you have daisy chained components to this, now imagine the case where you have components daisy chained over Aquabus. Power to EB832 is lost for whatever reason, and perhaps power to the head unit is lost. Now, the only thing providing power to all of your modules, including the head unit, including the display, including any other modules that you may have on the Aquabus port, is now powered by this little guy over a small, tiny, what is it, 36 watt, 24 volt power supply that the Apex sells for this. So notice what's going to happen to the power, to the voltage output as we increase our load. As we increase it to about 450. Now you're no longer even producing 12 volts anymore, 11 volts anymore. You're well under 11 volts. You're a little bit over 10. And the more you stress this little component, the faster it's going to fail. So the moral of the story is be very, very careful and very smart about how you actually connect all of your modules on Apex together. Make sure that you have strong power supplies powering a variety of this so that there is a failover. And you do not stress individual modules like this to power the entire chain of components, of entire chain of modules from just one small power supply over one tiny, poorly cooled buck converter that's inside this module and many others. I recommend that you do not put more than about 3 modules on one EB832. Clearly, no modules should be powered off of this port. Yet there is nothing preventing inside this module, there is nothing preventing other modules from being powered off of this guy, which eventually breaks this. From my previous videos and experiments, you've seen that it only takes a couple of minutes of high load on a module like on a buck converter like this to fail either temporarily or in many cases, as in this case, permanently. But in this specific repair, there is also a problem of assembly where glue ended up going onto the module, preventing the heat exchange and essentially frying the poor buck converter. This buck converter with proper heat exchange gets as hot as 70 to 80 degrees Celsius. 100 degrees Celsius is the boiling temperature for water. That's a very, very high temperature. When you have glue surrounding it, it's going to completely prevent any kind of heat exchange and it's going to fry it inside. Well, that's all for today. If you enjoyed this video, please like and subscribe, and I will see you next time.